Hello everybody. In the last session, we discussed how we go about getting the state equation of any circuit, whatever be the complexity, and then we discussed about what we want to do with the state equations, with the mathematical model. Once you have the mathematical representation of a circuit, you would like to analyze it. You would like to know the features of the circuit, the characters of the circuit, characteristics. All these you can obtain by studying the mathematical model. Previously, one used to do it manually by hand, plot the graphs or do the solutions of the equations by hand. All these bulwark today are done by software, and there are a lot of software available which make this job much easier, and then you can focus your attention more on interpreting the results and how to synthesize the circuits based on these results. So, therefore, in this session, in the previous session, this session and in future sessions, we will be using one particular software called MatLab. MatLab and Simulink. The MatLab Simulink environment is what we will be using, and we had a peek at this MatLab software in the last session. In this session, we will use that MatLab environment to obtain the waveforms in the various domains, the three domains, the time domain, the frequency domain and the pole zero domain. In all these domains, we will like to get the information of the particular circuit, but to the software what we are going to give as input will be the mathematical model in terms of the A, B, C, D matrices of the state equation. That will be our input. So, let us take an example. So, like in the last class, we shall take the example of the simple RC circuit first, and then work on a bit more complex circuits. So, this is an RC circuit which is having a VI source. You have a capacitance C and a resistance R here. And this circuit has a state variable which is Vc, and it has only one energy storing element, that is the capacitance, and therefore only one state variable Vc, and therefore only one differential equation describing the circuit, and that is dVc by dt. We have worked this out many times previously, minus 1 by RC. This is the A matrix into Vc plus 1 by RC. This is the B matrix into Vi. So, for now let us say Vc is the output voltage, the voltage across the capacitor that you want to see, and this is obtained like that, and there is no D matrix which is basically 0. So, we have to feed in the A matrix, the B matrix, the C matrix and the D matrix. These are the four matrices that you have to always feed in, whatever may be the system, because all the systems are described in the standard state space form, which is x dot is equal to Ax plus Bu, y is equal to Cx plus Du. And normally, to study the system in the time domain, the step response is a key response that gives almost all the characteristics of the system in the time domain. Okay, now that we have the state equation, we need to give values for the parameters r's and c's. So, let us give some values for this particular example. Let us say we take this as 10 ohm, and let us say we have a capacitance of 100 microfarads, okay, and then apply it and then see what is the responses. So, we would like to see, we would like to first plot the time axis and obtain the amplitude, of course. To we give an input Vi, which is a step, and if a step input is given, what happens to the output? This is what we need to study. So, output in this case is Vc and this is Vi. So, this is called the step response, and from this we can study various characteristics which we will look later on. So, now we go into the MATLAB domain. So, as I was describing yesterday, this window what you are seeing is the MATLAB command window. This is the main workspace of MATLAB, and this is where you will be keying in the commands and the functions, and the MATLAB operates as an interpreter. So, whatever you key in that line is executed immediately. So, here I will just open an edit window so that it becomes easier for us to key in the various parameters. I will just park it here. Okay. So, what are the parameters? We have parameters R equals 10 ohms for the circuit. I am not giving the units, just only the numeric value, and C is 100 microfarad, 100 into 10 power minus 6, which is E minus 6. So, R and C are given, and now I will define the A, B, C, D matrices in terms of the parameters, of course. So, now we have the A matrix, which is given by minus 1 by R into C matrix close, and the B matrix equals 1 by R into C matrix close, and the C matrix in this case is 1. We will see the C matrix will change depending upon what you want to monitor, what you want to sense, and we will probably sense some other variable later on and then see what happens to the C matrix and the D matrix. And the D matrix is in this case, for this particular output that you want to sense, that is the voltage across the capacitor, is just 0. Now, this is the model that you will be giving to MATLAB. So, let us copy this, and I will go to the MATLAB command space, give this model, and that is it. Now, the model is there in the MATLAB workspace. I will clear the screen just to know that all the variables are there. You see that A, B, C, D, R, all those variables are there. There is one particular issue. There are two variables here, C. One is for the C matrix, one is capacitance. So, we cannot mix the variables, and therefore, I will go and change this as C C1 instead of C, and we make this as C1, make this as C1, so that there is no confusion about the variables. And we again load the model and see what it is. So, now we have the A, B, C, D matrices, C1 and R are the parameters. Notice that MATLAB is case sensitive. So, it can recognize the difference between the uppercase and the lower case. Okay. Now, we do the first step in this analysis, which is the time domain. So, to do the time domain, let us see the step response. There are various responses that one can get, but for the purposes of understanding now, we will do the step response. So, to that we give the step function. I will input A, B, C, D matrices. This is the model, and let me also plot the grid. So, now on giving this to the MATLAB, it is supposed to execute and give you the output waveform. You see, this is the step, this is the unit step 0 to 1, this is a step, and you see that the waveform, the output is rising in this fashion towards 1. So, you have the amplitude, the time, you have the grid, you can read off what this is about 6 milliseconds, 6 in 10 to the power of minus 3. So, you can read of the rise time, that is around 90%, something like 2 to 2.5 milliseconds for this particular thing. Now, you can do a comparative study. For example, you can hold this plot, let us say hold this plot. So, the current plot is held, it is not disturbed, and let us change some of the values. For example, let us say instead of 100 microfarads, let us make this 10 microfarads. So, after having made 10 microfarads, we again load the fresh model to MATLAB, paste, yes, and then again we give step A, comma B, comma C, comma D along with grid. So, if we go back and look at the figure, you see that this was the earlier waveform blue, and in this green color you see the waveform that we now got with this changed parameters here. Now, we have reduced the capacitance C, and therefore, the time constant, the RC time constant is reduced, and therefore, this will be faster. So, you can expect it to be faster. You see that it rises to 90%, something like 0.25 milliseconds against around 2.5 milliseconds in this case. So, this is how one goes about doing the analysis in the time domain using the step response. There are various parameters, of course, which we would like to see. We will take up few examples, and you will know as we go about doing the examples what are the things to look for. And one of the important thing that I was saying is the rise time, and another important thing is how long it takes to settle down or reach steady state. And another important thing is this is a first order system, and therefore, there is no overshoots. There could be overshoots if you have LCs, the resonance effects, then you will see that this can overshoot like that and then damp out. So, these are some of the things that you will be looking for and trying to tune when you are doing your time domain analysis. Okay. Now, coming to the I would like to point out to you that you let us copy this figure, go to our notes, and let us insert the figure here. No, it is So, it is all right, no problem. Okay. We now go to the next part, which is the next domain, which is the frequency domain. Let me make some space here. We shall delete that. So, now in the frequency domain, we like to plot one is the magnitude versus frequency, the other is phase versus frequency. This will give you the total information in the frequency domain. Frequency omega is in radians per second, omega radians per second. So, one is the magnitude, let us say mag, and the other is the phase versus frequency. So, we would like to see a waveform. So, what is happening to the magnitude as frequency changes, and also what is happening to the phase as frequency changes. These are some of the issues that we would like to address. You see that there is a specific amplitude at this particular frequency. What it basically would mean is that if you apply an input, this is normally given in terms of gain or attenuation in dB. The input gets amplified by this gain or attenuated by this particular gain, whatever it is at this particular frequency. So, you can get the gains at various frequencies, and as frequency changes the gains are varying. So, almost all circuits will act as a filter in the sense that they give different gains at different frequencies. So, the gains change as the frequency changes, and that gives you a sense of the behavior for harmonics. So, for harmonics, what is the kind of output that you would get if there is distortion or a non-sinusoidal waveform or different frequencies at the input. Likewise, for the phase also, we would like to see what happens to the phase. It may be 0 phase to start off with, and then gradually go on and become 90 degrees at this particular spot, or minus 90 degrees depending upon the circuit or how you define the convention. So, these two together define your frequency response or the frequency plots, and this is generally obtained using what is known as the Bode plots. There are other frequency response plots, Fourier series plots, all those issues, but still the Bode plots gives you the frequency response plot for the circuit or the system. So, now we go to the MATLAB domain. We already have the ABCD matrices as given here. We again start with, let us say, 100 microfarad, the earlier one, copy that, let us paste it, we have the model. And now we want to see the frequency response. I will use Bode, A, B, C, D and the grid. So, it calculates and it gives a plot. You see, I told you that we are having two plots. One is the magnitude plot versus frequency. The other is the phase in degrees versus frequency. So, in this particular diagram, you see this blue line. This is the way the gain varies, the gain would vary as it changes. In dB means 20 log the gain. So, whatever the gain, the output by input, logarithm of that one into 20. So, 20 log base 10 the gain is the dB which is being plotted here, and this is. So, when you say it is 20 dB, you talk of 10 by 10 attenuation. Minus 20 dB means at this frequency there is a by 10 attenuation. Minus 40 dB means at this point there will be a 100 times attenuation. So, if it is plus, it is amplification; if it is minus, it is attenuation. So, this particular circuit does not attenuate at this. When you say 0 dB, during this portion the circuit does not attenuate, meaning whatever is applied at the input comes to the output, but as the frequency starts increasing, then it starts attenuating more and more, and as frequencies becomes higher and higher, it starts attending more and more. In fact, it is also evident when you go back to the circuit, have a look at the circuit, you see here this is a capacitance and we are talking of output across the capacitance. So, what is interesting is capacitance blocks DC. So, it has a very high impedance to DC. There is absolutely, it is like open circuit for DC. So, during the DC portions, that is during the DC portions here, this is DC portion. When the frequency is 0, it is DC, and when the frequency keeps increasing, it becomes higher and higher frequency. During the frequencies which are DC and close to the DC, there is this capacitance is something like an open circuit. Whatever you apply the input comes to the output. And during the portion when the frequency starts increasing still much higher, the capacitance starts giving lower and lower impedance. Ultimately, at very high capacitance, very high frequencies, this will act as a short, and the output will go towards 0, and therefore, the attenuation keeps going. So, that is how the meaning would be of this particular gain waveform. And look at the phase, that is, there is a phase shift between the input and the output. So, if you give a phase shift of some, if you give a particular waveform of some particular angle, with respect to the input, the output is not phase shifted at this near DC and 0 near DC frequencies, but the phase shift is gradually increasing in the negative direction because it is a capacitance, and ultimately goes to 90 degrees when the frequency becomes pretty high. This means that at very high frequencies, when it is truly behaving more capacitance and the resistance is swamped out, it is a capacitive load, and therefore, you have a 90 degrees phase shift. So, this is the meaning. So, therefore, both the magnitude and the phase is important when you have to discuss the response of the circuit to any input waveforms in the frequency domain. This is the Bode diagram or the Bode plot. So, now coming to the third aspect. What is the third aspect? The third aspect is on the pole 0 plots or the pole 0 domain. So, we like to also analyze the system in that domain. You should note that the system is the same, the circuit is the same, the parameters are the same, the circuit and the system is existing only in the time domain. However, you can view it in these three major domains, that is the time domain, the frequency domain, and the PZ or the pole 0 domain, to get many other characteristic information about the circuit, which will help you in tuning the circuits, designing the circuits much better. So, in the pole 0 domain, we like to get the plot of the S plane, this is the S plane, this is the omega axis, the y axis, this is called the sigma axis or the real axis. This is a complex plane. We can say sigma and j omega axis because it is 90 degrees phase shifted. Now, in this S plane, as I was mentioning last class, only the right half of the S plane is important. Sorry, I said right now. Only the left half of the S plane is important, as I have mentioned here. Important in the sense that all physical systems will have their poles and zeros located in the left of the S plane, because that is the stable region. This is the stable region. And the right half of the S plane implies that if you have a pole on the right of the S plane, you will have an exponent to the power of whatever a or b t, and then you can have a growing exponent which is an unstable condition, and that is why this region, the right half of the S plane, is called the unstable region. So, all physical systems that exist in nature have to be stable, and therefore, they will have their corresponding poles and zeros in this region and not here. So, if you by mathematical modeling find a pole in the right of the S plane, you have to make doubly sure that whether it is a physical system or not, because you are now dealing with an unstable system. And we probably will get most of the time a plot, the complex of the complex plane corresponding to the left half of the S plane. Now, let us see what are the things that will be plotted. One thing that you should note, that this is a system which has only one state variable, one differential equation, and therefore, there is only one root to the characteristic equation or one eigenvalue, and therefore, there will be only one pole, and that one pole will be on the real axis, because if you have a pole, a complex pole, then you have to have a mirror image also. So, then let us now look at the third domain, which is the pole 0 domain. Now, here again we go back here and see that we have the parameters. We take the model, paste it here, and then you have the model in MatLab. There is one function called PZ map, PZ map or pole 0 map. This is a function, and to that function we input the model A, B, C, D, and let me give grid. So, you see that the S plane, and here like I was saying, this is 0 and all going negative, which means only the left of the S plane, the right of the S plane is not shown here, because there is nothing there to show, there are no poles there. So, all the poles are located of course here in this left half of the S plane, and that is at this point. Are you able to see this blue X mark here? That is the location of the pole for this circuit. Now, this contains lot of course vertical and horizontal lines and also radial lines. What it basically means is that if there are complex poles, these radial lines indicate the damping. If it is on the real axis, it is well damped, over damped in fact, and if it is on these radial lines, there will be some oscillation before it gets damped, and there will be, in fact, these lines will indicate, as you start going towards the imaginary axis or the omega axis, you will have larger amounts of oscillations, but which will have a rate of decay which will gradually decay depending upon whatever the projection value is on the x axis. Now, let me just hold this plot and after holding this plot, let us change the value of the capacitance C1 to 10 microfarads. Let us copy that, paste that here. Now, you have the new model in place. Clear the screen. Now, just before that, we again look at the figure and then see that this pole is at minus 1000. And if you now see for the new model with changed parameters, you see that there is a pole here at minus 1000. The pole of the changed one, the one which you see here green in green, is at minus 10,000. It means that the pole is much further away from the imaginary axis, and therefore, it is faster. As the pole moves more and more away from the imaginary axis, the system becomes faster and faster. So, which means this system, which has the frequency in radians per second as 10,000, as compared to this system which has a frequency in radians per second as 1000, will definitely be 10 times faster. That is what we saw in the time response, where with the 100 microfarads you saw the rise time of 2.5, and in the case of the changed parameter where C1 was changed to 10 microfarads, you saw that the rise time was 0.25 milliseconds. So, there is the correlation. In fact, now you can place the pole accordingly, and you get the so that you get idea of what are these damping things. The character of this pole here, the overshoots would be 0%. If you place it here, damping is 1, frequency and the pole positions which will come in. So, you can position the pole accordingly on the pole 0 plane, and then get back what should be the R and C values such that you get this pole condition, and thereby you can design your circuits. So, this is an example that I showed you, that is the RC circuit. Okay. But probably you will have to try it out with more examples, but still however, I will probably do one more example with an RLC circuit, so that we get more familiar with the operation of the MATLAB in the 3 domains. Okay. We have already done the circuit, the RLC circuit also, that I am going to write down, which is you have a source, you have a resistance, you have an inductance, you have a capacitance, and there is another resistance across C, and this is the circuit that I was talking about, and then we had done this particular circuit. So, you have Vi, the source, you have R1, L, I will call this as C1 because it should not clash with the C matrix that we are using, and this is R2. And then there were 2 state variables, we had IL and Vc. IL and VC. Now, here I will write down the state equation directly, because this we had done before. Let me put it down as IL dot VC dot, this is the state vector x dot. We had a minus R 1 by L as one element, we had minus 1 by L as one element, you had 1 by C 1 as one element, and minus 1 by R 2 C 1 as another element. This is the A matrix. We have IL, VC, this is the state vector, plus we need to write the B matrix, which is 1 by L, 0, and VI. Now, the output, we will, let us say we would like to see the output of the voltage across the capacitance. We see our C matrix becomes 0, 1, state vector IL VC, plus the D matrix is 0 VI. So, this is our state equation that we have to input, and this is our A matrix, this is the B matrix that we need to input, this is the C matrix and the D matrix. Output is whatever we choose. Probably before we even re-edit this model, let me get back to the previous page here and just show you that it is very easy to have any other output. Let us say you want to have output here as IR instead of the voltage across the capacitance. IR would be the current through the resistance, which is same as the current through the capacitance, which is nothing but VI minus VC by R. So, this is nothing but minus 1 by R into VC plus 1 by R into VI. This is the modified output equation, where now you have to give this as your C matrix and this as your D matrix, not this. So, if you want to see IR as the output, we have to give this as the C matrix and this as the D matrix. Let us just have a look at that before we go on further with the other circuit, with the LC circuit. So, coming here and into MatLab, C becomes minus 1 by R and D becomes 1 by R, and that is it. This is the modified thing that you want to, nothing changes in the A and B matrix. What you want to see is only change going to affect the C and the D matrices. So, this is the model and you want to see the step A, B, C, D with the grid. So, you see the current, initially there is a high current because there is a step which is a high frequency, capacitor acts as a short, V by R. Initially there is no voltage across C, the whole voltage appears across R. So, 1 divided by 10 ohms 0.1 amps, and that starts exponentially decaying to 0 as the capacitor charges to full voltage. This is the nature of the current waveform through. So, as I was saying, you can see whatever output you want to see. Now, coming back to the circuit of interest now, which is the LC circuit. So, these are the A, B, C, D matrices that we need to input. So, let us go back to the editor here and edit these things. So, we need a parameter R1, and let us say we give R1 of around 1 ohms. We need to give L. Let us make it this fashion. L equals, let us say, 10 millihenry, which is 10 into 10 to the power of minus 3 or 10 e minus 3. C1 of 10 microfarads, let us have it, and then R2 equals, let us say, 10 ohms. And we need to modify the matrix here. So, we see that the A matrix becomes, there are 4 portions in the A matrix. Semicolon means the next row. Okay. So, these are the 4 elements that we want to fill in. So, you have first minus R1 by L. In the second position, we have minus 1 by L, and then we have 1 by C1, we have minus 1 by R2 into C1. So, we have the A matrix. The B matrix is 1 by L and 0, contains 2 positions. The second position is nothing but 0, but it is the second row. So, we have a semicolon and 0, and here it is 1 by L. The outputs that you want to see right now, of course, the C matrix 0 and 1, we want to see VC as the output, and the D matrix is 0. So, this is the model that we have, and let us take this model, copy that model, go into MatLab, let us clear all variables, let us clear the screen, paste this fresh model, and you have it. Just to check, we have A, B, C, D, we have the A, B, C, D, C1 parameter, L, R1, R2. Okay. Let me again clear the screen. So, let us do the step response. Step A, B, C, D, grid. So, this gives the step response, that is the output in this case is VC, the voltage across the capacitance. So, the voltage across the capacitance would behave in this manner if you apply a unit step of 0 to 1 like this at the input. So, you see that there is an error as I start going to the steady state, the remaining voltage is dropped across R1. If you look at the circuit simultaneously, you will see that here the voltage is 0. Initially, capacitor is a short, inductor is open, all the voltages will be dropped across this, and 0 voltage here starts with a 0. Then as time progresses, the capacitor gets charged through the current here and the voltage builds up, the voltage starts building up, and in the steady state, that is in the DC condition, capacitor is open once it is fully charged, and during that time R1 and R2 share, because this is 1 ohm and this is 10 ohm. So, 10% goes to R1 and the remaining 90% goes to R2. So, this is how one, and the rise time is as given here. So, it takes roughly something like 4 milliseconds to reach 90%. Now, let us see what happens if we change the parameters. So, let us change this R2 parameter, let us make it higher, let us say 100 ohms. So, this 100 ohms we copy, go to MatLab, paste that one, and this is the new model. Let us hold the previous plot. So, the previous plot is held, and then again we give step A, comma B, comma C, comma D, and let us see the grid. So, now if we see the figure, you see very nice and interesting. This was the earlier figure, nicely damped, no oscillations. The moment we change the parameter R2, you are having overshoots beyond 1, and then gradually it is damping to 0. It rises quickly, but shoots beyond the 1, beyond the value 1, and then you have damped frequency of oscillation as shown here. Now, what is causing this? From the time domain, it may not be so very evident. Probably we may have to look at the frequency domain and the pole 0 domain. The pole 0 domain will give a very interesting result. This here, you will see that the poles. Now, here there are 2 energy storage elements, therefore, there are 2 state variables, and therefore, it is a second order system, therefore, there will be 2 poles. So, the number of energy storage elements is going to directly influence the number of the poles. So, if there are n energy storage elements, there will be n poles. So, there are 2 energy storage elements. This, in this situation, both the poles should be somewhere close to the real axis or on the real axis. And here, because you are getting overshoots, you will see that the 2 poles start moving towards the imaginary axis and they become complex. One is at the positive off and the positive upper, and one is at the lower portion, which is the negative. One indicating capacitive effect, one indicating the inductive effect. So, if you have any such oscillation, you should have 2 effects, which is the capacitive and the inductive effect, which is what we are having in the RLC circuit. So, this is the interesting point that you will see once you just keep varying the parameters. Let us look at the frequency plot also. So, let me go back, let me start in the same way. We had the original 10 ohms, let us put back that model, copy, I will paste that model in MatLab, and we have the model there. Let me put Bode, A, B, C, D, grid. So, this is the Bode plot. Now, one thing that you should notice here is that, of course, though it looks very similar to the RC circuit, the slopes are different. Here the slope is for 1 decade from here to here, it has gone down by 40 dB, whereas in the earlier circuit for 1 decade from here to here, it would have gone down only by 20 dB. So, the slope was minus 20 dB per decade, whereas here it is decreasing at a much faster rate. So, it is a much sharper filter. And then look here, look at the phase waveform. It starts with 0 and then it's gradually moving towards 180 degrees, because you are having the inductance and the capacitance, and they provide the 180 degrees phase shift, because one pole goes up, the other pole goes down, and then you are having a 180 degrees phase shift between them, and that is what is causing. So, two poles, each pole is going to add a 90 degrees phase shift. There are two poles, and therefore, there will be 180 degrees phase shift, and each pole is going to add a slope of minus 20 dB per decade filtering action. There are two poles, and therefore, there will be minus 40 dB per decade filtering action. That is, let us now freeze this plot. Let us hold the plot, and let us change the parameters back again here. Let me make the R2 as 100 ohms instead of 10 ohms. Let us copy that, paste it in MatLab to get the new model, and then again see the Bode plot. Bode A, B, C, D and grid. I want to look at the grid. Now, look at the figure here. You see something interesting happening. This is the earlier one, the blue waveform. No problems. There were no, because the two poles were quite close to the real axis, and once the poles start shifting away from the real axis, it is going to peak. There is a resonant action here, and that is peaking, which is giving an amplification of the gain, and goes down. And you see the difference also in the filtering action. This is a much better filter compared to the earlier one. With this falls much more sharply to in phase by 180 degrees to 180 degrees. So, it is not a gradual change in 180 degrees, but magnitude filtering wise they are more or less the same, because they are going to have the same minus 40 dB per decade, but phase wise it is going to jump quite fast to 180 degrees. Now, this resonant action is basically because the poles in the pole 0 domain, that is in the S plane, you will see they have become complex poles. From a real pole they have become complex poles because of the change. We could probably see that. So, let us see the third domain also. Let me first show you the earlier domain. We make R2 10. Let us copy that. Let us paste that here. We have the model. Now, I will make PZ map A, B, C, D, and we need the grid. So, you see there is one pole here at the frequency of 1000 minus 1240 at this point. Damping is 1, you see it is on the real axis because there are no overshoots, and then there is another pole here at frequency of around 8860, again damping is 1, no overshoots. Now, let us freeze this and see what happens. You see there are two poles, there are only just two poles. Let us see what happens when we take the second case, when the output resistance, that is R2, is made larger. So, which means there is now some oscillations which is going to occur between the capacitance and the inductor. It is now going to act more and more like a resonant tank. That is, when R2 becomes totally open circuit, it is just pure LC, because R is just 1 ohm. So, it is an LC tank, and therefore, it will start oscillating more and more. So, which means these poles will start moving up and below. So, you will have one pole here and one pole here, and they will start moving towards the imaginary axis more and more as you make R2 higher and higher. So, let us have a look at that. First, let me freeze this plot, hold. So, this plot will be held. Let us go to this, let us change R2. Now, R2 is made 100 ohms. Let us copy that, go to MatLab, paste that in MatLab, and then again I will give the PZ map A, B, C, D, and then I want to see the grid along with the grid. So, now let us have a look at the plot. So, you see the plot here. This was the earlier plots on the real axis, and now these two poles, the green ones, are the ones now after having changed the parameter R2. So, as R2 starts going towards infinity, these two poles are will become complex poles with a mirror. That is why the 180 degrees phase shift, and they gradually start moving towards the imaginary axis, which is this axis, and become more and more oscillatory. So, this phenomena, you see that this phenomena which is exhibited in the time domain gets reflected. The same phenomena can be viewed in different ways in the frequency domain and the pole 0 plots, and this will give you exactly what you want to do for design by if I want to place the poles at any specific points for specific circuits for specific applications. So, you see that the circuits that we have been discussing and also the models that we modeled last class can be in the last session, we can put them in model, input the A, B, C, D matrices and view the performance, view the character, view the characteristic features in the three domains, that is the time domain, the frequency domain and the pole 0 domain. And note that all these three domains are going to give you very useful information about the circuit, even though the circuit and its responses are always existing in the time domain. The variation of the gain with frequency is not very evident in the time domain. The bandwidth is not so very evident in the time domain. The pattern of the pole 0 which will give you oscillation or which will give you that amount of damping is much more easily understandable looking at the pole 0 plot. In fact, the pole 0 plot you can position, this should be the damping, this should be the position of my poles, and work back and then evaluate what should be the value of LCs in the circuit, and that will be useful for design. So, any circuit can be modeled, and once it is modeled, that can be simulated and analyzed as we have shown here. So, with this, let us conclude the discussion in this session. Thank you.